Much, David. Thank you all for coming on this Wednesday evening to hear about particle physics. And there's going to be a change already on slide one. The title that I gave the Simons Foundation was Collision Course. And in fact, that was a title that I started using when I got funding from the Simons Foundation to go on sabbatical. And during that sabbatical, I really cemented my interest in using machine learning for particle physics applications. And what I realized is that particle physics and machine learning, they're not just on a collision course, they've really collided. And now we have a new generation of scientists, what I'm calling Centaur scientists, who really think like the mythical creature, the Centaur, that's half horse, half human, really thinking half physicist and half a machine learning expert. And this name Centaur science comes from Centaur chess, if people have heard about that. When the rise of computer chess was going on, you had a situation where, while it was true that machines were starting to outclass humans, there was a period of time when humans using machines were outclassing the machines by themselves. And still, that's the idea that I have in my own research, that by combining together knowledge from the physics community and the computer science community, that we can make great advances. And I just want to thank the Simons Foundation for helping me go in this new research direction. So as I said, we're on a collision course. I am a theoretical particle physicist, but my friends at the Large Hadron Collider smashed together particles, and out comes amazing discoveries, most famously the Higgs boson discovery in 2012. This particular image here is of a collision that gives you jets. These are these collimated sprays of particles, which are a focus of my own research, and I'll tell you a little bit about what jets are and how we can analyze them. But again, there's this other collision that's going on, a collision between the high-energy physics community and the communities of mathematics, statistics, and computer science that I first got a chance to see at the Aspen Center for Physics in January of 2019, and realizing that people from these two communities were asking similar types of questions and working on similar types of techniques. And indeed, for my case, new insights in particle physics facilitated by these advances in machine learning. And of course, it's not just particle physics anymore. Many scientific fields are being influenced by machine learning. And it's not just machine learning. In some sense, it's more general statistics, computation, new ways of using computers for discovery. So in my own work, this has been an absolutely smashing success. And just thinking about the things that I've done over the past 5 years, things that I knew I was going to work on, and some things that I didn't think of. So for example, I'm a theoretical physicist, and somehow I got interested in the mathematical structure about how you calibrate a detector. And that's what machine learning can do to a theoretical physicist's mind. So I'm not going to be talking about these examples, but want to give you some examples from my research. And I'm actually going to be talking about recent research. About one work that is going to be presented at NeurIPS next week, and one work that's not even published. And so somehow in this public audience, I need to navigate this and giving you kind of a colloquial understanding of what's going on, but also a little bit of technical detail to satisfy myself about this work that I'm pretty excited about. I'm excited about my own research program, also excited about this institute that I direct, the Institute for Artificial Intelligence and Fundamental Interactions, funded by the NSF, joint between MIT, Harvard, Northeastern, and Tufts universities. And as a slogan, taking this deep learning, or AI, and combining it with, in quotes, deep thinking of fundamental principles in physics to both gain a deeper understanding of physical systems, but also a deeper understanding of the nature of intelligence itself. And this efforts are really being driven, so thank you for mentioning mentoring, really by this next generation of talent that's working in this AI plus physics space. And in our institute, which we call IAIFI, we have these postdoctoral fellows who work on a variety of things at the intersection of physics and machine learning. And now they're going on to awesome jobs in industry and in academia. And we're trying to train this next generation. And this past August, we had a wonderful summer school and workshop. You can see the summer school participants very happy doing hands-on tutorials to try to learn about these new techniques aimed at physics discovery. So trying to talk about AI plus physics became a lot easier this past year. People were very skeptical. What is this mashup of AI plus physics? But our friends in Stockholm helped us out. And recognizing that AI plus physics really is in some sense a discipline. And also just kind of AI plus science more generally, the impact that you can have by bringing together these communities. And realizing that learning, which we often think about as something that's based in the neuronal structure of our brains, that also there's a way of thinking about learning in the context of dynamical systems. The power of doing statistical reasoning, not deterministic reasoning like we teach our first-year physics students, what we do in our second-year physics students, of statistical mechanics, quantum mechanics, that's actually a better way of thinking about processing information in the world. and then its broad implications for scientific discovery. And so what I want you to come away from this talk today, whether or not you understand any of the technical details that I might talk about along the way, is this idea, these lessons that have come from the collision of my community, and thinking about what the lessons might be for your own community. And what I would say for particle physics or high energy physics, that to meet the standards of scientific rigor and performance, we need to teach machines to think like a physicist. Do I need to do anything to get the screen back? Great. And what does it mean to think like a physicist? Well, an example is to think about symmetry structures. And we're going to be seeing space-time symmetry appearing in this talk. We're thinking about the ways that particles look if I travel close to the speed of light, energy and momentum get scrambled up, and thinking about how that impacts the decisions I might make with the machine learning algorithm. That's going to be helpful. Systematic uncertainties, guarantees of exactness if you're doing a theoretical calculation, doing statistical inference. Those are the things that we need to bake into our machine learning architectures. But grudgingly, I've had to accept that also there's a value in physicists learning to think like a machine. And to fully capitalize on AI technologies, we really do need to teach physicists to think more in this computational language. And things like computational complexity, or thinking about your problems in the language of optimization, or search over large spaces, or just algorithmic reasoning in general. This is something that certainly I was not taught when I was a PhD student, but now seems to be pretty essential to take advantage of these technologies. And putting these things together, this is this title, the Centaur science, that progress in computation and information theory, it's long been intertwined with progress in the physical sciences. Statistical mechanics has an understanding of thermodynamics, but also an understanding in information theory. Quantum computers, whether or not we can ever build one, thinking about quantum problems has helped us think about the limits of computation, even in a classical regime. And so this Centaur science approach is what I want to be telling you about today. And so for the rest of this talk, I'll give you a little bit of a brief particle physics 101, as well as a machine learning 101, and telling you why deciphering collision debris requires statistical inference, and that's well matched to this Centaur scientist approach. And then I want to give you these two case studies. One, which roughly speaking, you could think about taking a machine learning architecture that's very famous, called a transformer architecture, really kind of dominating machine learning these days, and teaching it how to think about physics symmetries, and in particular something that's known as Lorentz boosts, so giving transformers a boost by building in symmetries into your structures. And then riffing off of the recent Nobel Prize, thinking about QCD, that's the theory of the strong interaction, quantum chromodynamics, and thinking about how you might do theory calculations enabled by thoughts in information theory. And at least for me, when I, as a physicist, have thought about like a machine, I can translate my problems into a language that is then just kind of an optimization that I can throw at a computer and get an answer. So these are the case studies that I'm going to be telling about, again, from relatively recent work. So I'm going to try to have some cartoon level stuff, but also a few technical details for the experts in the audience. OK. So the standard model of particle physics, cemented in 2012 with the discovery of the Higgs boson, is often depicted like this. We have a pinwheel of the quarks in the standard model in orange, the leptons in green, the force carriers in blue, and the Higgs boson at the center of the standard model. And this is an extremely misleading picture, because it makes you think that you've actually seen these particles in real life. And you have not seen these particles. Most of the time, you've just inferred their existence from other impact that they have on your experiment. So the ones that you actually see directly are the ones that carry electromagnetic charges. So those are photons, muons, electrons. Those really do hit your detector. Everything else in this pinwheel has to be inferred. My own area of research is focusing on the strong force and the quarks and gluons of the standard model. They confine together. And because they confine, you cannot see them independently. All you see are these composite states with funny names like pion, kaon, and more familiar protons and neutrons. And then other elements in this pinwheel, you can only infer them either by their absence, in the case of neutrinos, that just sail right through your detector, or for the heavier particles like the top quark, Higgs boson, W, and Z boson, and to a lesser extent the tau lepton. These are things that decay, and so you can only infer them from their decay products. So inferring, statistical inference, that's really the name of the game when you're doing particle physics. And it's worse than this. Things don't come and hit your detector with names, flags that say, here's what I really am. What you really have is you have a heterogeneous detector that is reading out information every 25 nanoseconds, basically like a megapixel camera taking pictures of this collision debris. And you have sensor hits in tracking, calorimetry, muon systems. Somehow you have to infer what's going on in fundamental physics from this collision debris. And again, the area that I study, these jets, these collimated sprays of particles that are depicted here in these orange cones, these are manifestations of quarks and gluons, but they are themselves not quarks and gluons. They are something that I can infer their existence from the detailed patterns of the spray of radiation that I get. So I spend my life thinking about these jets, sprays of particles, and trying to infer, based on their properties, what the fundamental description is. Is it the standard model of particle physics, or is there, for example, evidence for some new phenomena? And one of the things that makes particle physics particularly challenging is that one of these jets carries no information by itself, that you need an ensemble of jets to actually do inference. But again, that's very well matched to the Centaur scientist machine learning plus physics approach. Okay, so that's my particle physics 101. Now, machine learning 101, here I'm going to show a somewhat technical slide about one of the basic tricks that's used in machine learning to do inference. So this is known as simulation-based inference. That is, you have some trustable training data set, usually synthetic data generated in some way. And there's a trick that's known as the likelihood ratio trick that allows you to use machine learning optimization to estimate ratios of densities. So if you're trying to decide, hey, is that jet spray a quark or is it a gluon? Or is that standard model physics, or maybe it's something beyond the standard model? The way that you want to assess that is you want to estimate a likelihood ratio. And if you want to estimate that likelihood ratio, if it's more likely to be the p-type versus the q-type explanation, you can do that by taking training data where some synthetic data, or maybe even a real data set, you sample from that, sample from p, sample from q. And then if you give me a learnable function, some, let's say, neural network that has a number of parameters that I can optimize, and I compute a loss function, in this particular case, a loss function that's taking the logarithm of that function over the p data set, and then f minus 1 over the q data set, and then try to make that thing as small as possible. What you can show, if you take a class in statistics, is that you can show that asymptotically the minimum really is this likelihood ratio, and the value at the minimum for the statistics experts is the so-called KL divergence, which is a measure of similarity between data sets. So if you're like me, and you encountered this, your kind of eyes are glazing over, you're saying, oh man, this statistics stuff is really hard, how am I ever going to understand this? But again, the Centaur scientist approach, and say, well, actually, what am I really doing here? I'm taking a function and I'm optimizing it. When have I ever learned about functions and optimizations before, again, wearing my hat as a physicist? And this is what we teach our students when they take an advanced classical mechanics class. So in the first mechanics class, they learn F equals ma, that's Newton's law. But eventually, they learned that actually the way to derive F equals ma is through this framework of Lagrangian mechanics, where you extremize an action, and that gives you the equations that govern classical physics. And in this case, actually asymptotically, I can build an action. That Lagrangian just happens to be dependent on these functions. And the Euler-Lagrange equations, that's the generalization of F equals ma. Solving that, the solution is P over Q. And this is something that a second-year student at MIT can do in 2 lines, this derivation. And what I mean by asymptotically is this is asymptotically if you had infinite training data and infinitely flexible neural networks, perfect information. Of course, in real life, you don't have that, which is why you need to rely on statisticians to help you out. But this is an example of this multiple viewpoints on a problem giving you insights into the structure, in this case, physics insights into the structure about how machine learning optimization works. But it requires the shift in focus from solving problems to specifying them, and then offloading it to a machine to do the actual optimization. So examples like this, once I realized, oh my God, it's just Lagrangian mechanics, I'm a theoretical physicist, I can do this. I kind of transitioned from being an AI curmudgeon to then this AI evangelist. It also helped to get the NSF to fund me. That definitely helps the transition. And we were funded, IAIFI, in August of 2020, and Dennis Overby from the New York Times called me up in November of 2020 and asked me the provocative question, can a computer devise a theory of everything? And this is the direct quote from the New York Times article, so you can tell my exuberance at the time. So let me just quote myself. So this is what I said. I said, in 5 to 10 years from now, I'm going to want to do exactly what you're getting at. Here's the data. Here's a very rough toolkit. Find the equation I could put on a T-shirt, the equation that replaces the standard model of particle physics. What's the equation that replaces Einstein's general relativity? I said this in November 2020, and my friends really laughed at me. And they said, come on, Jesse, this is insane. What are you thinking? That this is not the way that theoretical physicists operate. And then ChatGPT was released in November 2022, And then people are saying, Jesse, why haven't you done this already? Don't you know that you have the power of these large language models? Why don't you just have the large language models process all the particle physics data that you've ever seen, all the information on the archive, and of course you're going to come up with the theory of quantum gravity. Which actually there are researchers associated with the Simons Foundation who are trying to do something roughly along those lines. And it may be that the answer to life, the universe, and everything could come from one of these foundation models trained on vast amounts of information. And I'll show you one example where I've had to change my mind about what language models can do for fundamental physics. But, okay, this exuberance aside, what I've seen is that if you take the Centaur sciences approach, you're really trying to attack things from both angles, that you just end up asking different questions than you would have asked before, even if it isn't this future where a language model can tell us what the answer is. You end up doing things in a different way. And so the last time I was speaking in this room, I was reporting on the story that was this 5-year effort about revisiting the strong force and revisiting quarks and gluons. And this is a heroic effort, which I'm not going to tell you about today, but it was trying to say, hey, quarks and gluons, you told me that individual quarks and gluons can't be distinguished. Yet I want to understand the properties of what quarks and gluons are. And we wanted to use this using public data from the Large Hadron Collider. And using this likelihood ratio trick, plus a bunch of other tricks, including things that you can ask me offline, why I have a cute little panda. It's not a panda, that's a koala on the screen. And then with essential contributions from amazing AI plus physics talent. And so 2 of my former graduate students, Patrick Missy and Eric Metodiev, Eric's actually in the audience today, really led this effort to help us revisit concepts from jet physics, from QCD, through this machine learning lens. And the thing that I showed in this room the last time was this depiction where I never need to make any theoretical mention of quarks or gluons, that from the machine learning out pops actually a data science-y way of saying what is the difference between a quark and a gluon. So on this axis here, this is a measure of complexity. And on the axis here, on the x-axis, is a measure of the energy scale at which I'm probing things. And so if I probe things at very high energies, what I see are individual quarks and gluons. That's a very low complexity situation. But as I go to lower and lower energies, I see the emergence of structure, these pions and kaons coming out. And in fact, you can see that the rate of growth of that complexity depends on whether I'm talking about quarks versus gluons. Again, purely data science way of talking about a concept in fundamental physics. And in fact, the ratios of these curves correspond to numbers that appear in the Lagrangian of quantum chromodynamics, and you can extract that from a purely data science way. So this is a fun story that did a few years ago. I'm going to tell you a different fun story today. But again, this is just an example of this rise of these Centaur scientists who are synthesizing physics intelligence together with artificial intelligence. Okay, so next thing I want to do is I want to tell you about the submission that we're going to be giving to NeurIPS next week, or accepted in NeurIPS next week. And this is an example of a fun collaboration, because it was a collaboration between academics and industry partners, in particular 2 folks who were at Qualcomm at the time that this work was done. And it's really interesting interacting with folks from industry, but thinking about how you might actually attack particle physics problems. So here is a simplified version. So this is from figure 1 of our NeurIPS submission. This is the simplified version of the analysis pipeline at the Large Hadron Collider. So one thing I should just say at the start is that machine learning, in particular shallow machine learning, and low-dimensional statistics, this has a long history in high-energy physics. It's not like we've just rediscovered statistics in machine learning. People have been doing this for many decades. It's just that every aspect of collider physics is being revisited through the lens of this deep learning architectures or high-dimensional statistics. That's what's new. And what we're taking advantage of is we're taking advantage of the availability of vast data sets, trustable simulations. That's what's driving these advances, such that I can take real data coming from nature, which apparently is an octopus, nature, having it pass through my detector, reconstructed. These jets that I talked about were identified. I select events that I think are interesting. And I can do exactly the same thing with synthetic data based on quantum field theory calculations. I calculate scattering properties. I do non-perturbative modeling of the process by which quarks and gluons come together to form these bound states. I simulate my detector, and again, reconstruct event selection. I do the inference that I talked about before, likelihood ratio analyses to try to infer the way that things are working in nature, and then, of course, leading to discoveries and measurements like the Higgs boson discovery. So this is the analysis pipeline simplified. And now if you're someone who thinks about machine learning, you want to know, for each of these green boxes, can I attack it with machine learning in some way and do a better job. Either do a better job in inference, or maybe doing a better job in quantum theory, better job in reconstruction, better job of sampling my configurations efficiently. That was the thing that we wanted to do with our friends at Qualcomm. Now, from the machine learning perspective, the juggernaut in the machine learning world are things called transformers. Transformers are a type of AI architecture that's taking over the world. And while it's true that every neural network is basically just kind of some fancy function approximation that eventually I'm going to optimize to do some task, certain fancy functions are fancier than others and more powerful than others, and transformers turn out to be one that's particularly powerful. So a more standard neural network that you might have heard of called a feed-forward neural network, that's based on linear transformations, it's based on nonlinear activations, and it's done an incredibly good job in general. But these transformers have an extra ingredient in them. And at a cartoon level, what transformers can do, which more traditional neural networks or feed-forward networks can't do really, is that they can multiply. Now, why? You think multiplication is a pretty basic operation. You can ask, why do we only now think to do multiplication? In fact, people have thought about multiplication for a while in the context of visual sensing, that if I'm trying to look at a scene and I'm trying to make decisions about what's going on in the scene, I don't want to be overwhelmed by all the information coming at me. So if I multiply by 0 in regions that I want to mask out and 1 in regions that I want to pay attention to, that is a thing that can help if I'm doing visual sensing. And attention mechanisms they incorporate multiplication as a primary operation. In this example I gave you in terms of masking, but we'll see other examples in particle physics in a second. And these particular things of transformers, they use something that's called dot product attention. The details don't matter, but something that works and scales incredibly well empirically and has given rise to a large number of advances. And I should say, multiplication is something that appears elsewhere. And my student, Rekab Gambhir, has been thinking about alternate multiplication schemes that are relevant for particle physics. And indeed, it's true. You add multiplication into the mix, and your performance improves. OK, so what can you use transformers for? Well, one of the things you can use transformers for is to make an April Fool's joke at your IAIFI director's expense. And so everyone has heard about ChatGPT, but have you heard about ChatJSCT? And so this is taking ChatGPT, natural language processing based on transformers, with clever prompt engineering, and you can get me, they, I don't know, to speak in my tone of voice very confidently about various things. So I asked it myself, what is a transformer in the context of machine learning? And it says, a transformer in the context of machine learning is not a robot in disguise, but rather a powerful neural network architecture commonly used in natural language processing tasks. Named after its ability to transform input sequences into output sequences, transformers have revolutionized the field with their attention mechanism, allowing them to weigh the importance of different words in a sentence when making predictions. So you can ask whether my description of transformers versus its description of transformers, what was more informative. But this one always says what its name is, always likes to connect it back to fundamental physics. And this last sentence is coming back to my quote in the New York Times. If only we could use transformers to decode the mysteries of the universe as easily as they decode language. And maybe that's one aspirational dream for the community. So that's one use of transformers. Of course, this was an April Fool's joke. But then we realized, why stop with mimicking me? Why not actually start using this as a way to do public outreach? And so at the Cambridge Science Festival, a similar type of prompt engineering was done to mimic Marie Curie. This is IAIFI fellow Gaia Grosso, who did the prompt engineering to make they interact in the following way. And what's interesting here is that the prompt engineering was done in order to make sure that Marie Curie didn't actually know about AI, because of course it was before her time. And so just this quote, "Why is it important to fund AI and science?" And Curie says, while I'm not familiar with the concept of AI or artificial intelligence, as it is beyond my time, I can certainly speak to the importance of funding science. Science is the key to understanding the world around us. It is through scientific research that we've been able to make significant advancements in medicine, technology, and various other fields. And then as for AI, if it is a scientific field, I would presume that funding it would have similar benefits, allowing for advancements that could potentially benefit society in ways we cannot yet imagine. And so the people at the Cambridge Science Festival had a lot of fun interacting both with real physicists, but then also with this AI avatar. And it's a really fascinating way of communicating and really engaging way of communicating science. Now, what about using transformers for scientific applications? And one thing that did with an IAIFI fellow, Siddharth Mishra Sharma, as well as a talented, actually high school student at the time, Yidang Song, is to use transformers to process astronomical data. And I am not an astronomer. And so this is a really interesting case of me going into another field and asking, as a novice in this field, can I take the data from that field, process it using something like a transformer, and actually learn something about the way that the universe works? And so what's done in this particular paper that was submitted to the Conference on Language Modeling is you use two types of transformers. One transformer that's going to take images from the Hubble telescope, use a transformer to embed it into some mathematical representation. And then those Hubble images are accompanied with the proposal abstracts used to justify pointing the telescope at that particular part of the sky. And then you can do that, and then you can put it into a language model. And then you can align the text, the text representation and the image representation, put them close together if they came from the same image abstract pair. And that is a model that then gives you correlations between concepts as encoded in text and images as encoded, obviously, in images. And I was very skeptical that this would work at all, that you could, for example, go into the space and then like pick a random image as encoded in this particular way and then say, hey, what is that image actually a picture of? And I was shocked about how well it did. So here's an example where I, as a novice, got it wrong, as did an off-the-shelf AI. So this is a picture that Hubble took of this image here. And what I saw, and an off-the-shelf machine learning model saw, is we saw a ring. And maybe people have heard about Einstein rings. So you take an Einstein ring, that's some kind of circle, right? Now this must be an Einstein ring, that must be a gravitational lens. But of course, you then use the information coming from this proposal abstracts, and when it sees rings like this, and especially they're a little bit squashed, it says, no, that's a supernova remnant. And then if you actually go back into the underlying training data, this is actually a proposal from the supernova 1987A intensive survey. That was their proposal to search that part of the sky, and indeed, the correlation as found by these transformers was able to make that proper inference. And so I was actually kind of blown away about how well this did, because if you actually look at the actual abstracts, they're kind of messy, they're not in a common format, but this is the power of transformers to process even textual data. Now, what about transformers for particle physics? Can you do it? Of course, someone has done it. But then you go into the details of the first implementation of a particle transformer, and you realize, oh wait, they are not thinking yet. Oh, they're already thinking like Centaur scientists, but they had to hard code it in. There's this extra little thing called interactions, hard-coded physics knowledge necessary to get the right performance. And come on, we should be able to do better. It should be able to tell the machine, hey, here are the concepts of fundamental physics. Use those concepts to don't hard code the knowledge, instead just learn the knowledge from some more primitive features. And as I mentioned, one of the most primitive features that we have in particle physics data is symmetries. So let's use symmetries to enhance transformers. But I need to do symmetries in a way that I can do multiplication. Okay, I want to do space-time symmetries, but I want to do multiplication. And you ask people who study space-time symmetries and the definition of multiplication, and they will say, oh yes, I can have a principal way of multiplying particles. Let me take space-time symmetry, also known as Lorentz symmetry, build an equivariant network. What that means is that I can do a transformation on the data and then make an inference, or I can do an inference and then do a transformation of the data, and I get the same answers. That's saying that I have the proper symmetries encoded, and people have built neural networks based on that. And then what is multiplication? And I don't know if anyone in this audience has taken a quantum mechanics class. When I teach the third semester of quantum mechanics, this is the part of the course that the students hate the most. So it's called the Clebsch-Gordon maps. And this is how you take the A+ student, and they get an A in the course because they don't really understand the Clebsch-Gordon maps. And it does not look very fun. Putting that into a transformer doesn't seem fun at all. People have tried to do it, but it's kind of a challenging bookkeeping task. Again, one that can be accomplished, but one that doesn't satisfy also what a physicist wants, some intuitive notion of kind of simplicity. Okay, so what are we going to do? Centaur science approach. We're going to look to physics. And where are we going to look to physics? We're going to look to physics in a very weird place. Okay, this is going to come out of left field. This semester, I am teaching a course on supersymmetric quantum field theories, and intuition is going to come from that field. Supersymmetric quantum field theories, why do you do that? What is supersymmetry? Supersymmetry is a symmetry, a hypothetical symmetry that relates bosons and fermions. Bosons and fermions have different quantum properties. Bosons are ones that you can stack a bunch of them into the same state. Fermions are ones that don't want to occupy the same state. Very, very different objects. Supersymmetry is a symmetry that relates those two together. But you like to do manipulations in quantum field theory that somehow treats them on an equal footing. So you need to find some way of putting these things that look dissimilar and putting them together. And the trick is to do supersymmetric calculations in superspace, where what you do is you take a boson, you add it to a fermion, but you put this extra placeholder. This placeholder itself is fermionic in a way that this combination actually has bosonic properties. And then this superfield is something that I can freely add and multiply, and this is what I teach the students in my class. And if you'd like to come to MIT at 10:30 tomorrow morning, you can learn about this. But the trick is to introduce a placeholder with well-defined transform properties, and then all the multiplication rules just fall out. And so what does that look like for space-time symmetries? What's the analog of this superspace coordinate for space-time symmetries? And the analog, and now we're like deep in the technical weeds, the analog for that are the gamma matrices that come from the Dirac equation. And so the suitable placeholder for the Lorentz group, this also goes under the name of the space-time algebra. The placeholder are gamma matrices. Gamma matrices have really fun rules for how you multiply them themselves together. And if you take 1, 2, 3, 4 gamma matrices, that allows you to put scalars, vectors, antisymmetric tensors, axial vectors, pseudoscalars, things that have different space-time transformation properties. They can all coexist into one object. That can be multiplied as much as you want to do in the context of a transformer architecture. And so this is a work led by Jonas Spinner and Victor Brezzo, along with our collaborators at Qualcomm and at Heidelberg universities. And okay, now this is just a slide just for me, which is to say, and we get amazing performance. So this thing is called Alligator, Lorentz equivariant geometric algebra transformer. And so the green curves here in Alligator green are just showing, in this case, down is better, up is better. And okay, the details of this don't really matter. Excellent performance across the LHC pipeline. For me personally, this is a little bit sad. So my best attempt back in 2019, when I was converted into becoming really excited about this, my best attempt at telling the difference between a signal and a background having to do with jets, I got some performance, and then this new technique that has the symmetries built in. Oh wait, you put the symmetries built in, you put it in domain knowledge, and you get a factor of 3 better performance. And that's the type of thing that we've seen over and over again. You put the physics into the machine, better performance, but also more interpretable, and then connections to fun things like supersymmetry. Okay, so state-of-the-art results, but it's a Centaur-style merging of physical and computational structures, because I need the physical structure of space-time symmetry. I need to know that I can talk about space-time symmetries in terms of scalars and vectors and whatnot. But I need a computational structure. I need this multiplication to take advantage of transformer architectures. Finding a way to put those things together gives something interesting. And again, you can think about this in your own field. What is the intuition from your own field, or the knowledge of your own field that you can synthesize with computational knowledge and make progress? Okay, so the last example that I want to do has to do with QCD theory meeting information theory. And I'm going to skip over a little bit of an interlude just in the interest of time, but just saying that computational complexity, thinking about how you do computation, this is something that has been a muse for me. And it turns out that if you think about how you do a computation in a more efficient way, often the more efficient way of doing the computation also gives you physics insights. And so I don't have enough time to tell you why computational insights have led to cool visualizations of jet physics like this. You can ask me offline what this picture is. But faster computation can lead to better science. That, I think, is not controversial. Okay? At least I hope it's not controversial. Good computation, good science. Which somehow implies I'm going to talk about something controversial. And yes, I will. Unfortunately, he's not in the audience, so he can't defend himself. But here in the New York area, David Hogg and Solad Villar wrote an inspiring / infuriating paper, inspiring and infuriating in equal parts, about this kind of thinking like a machine and the dangers of thinking like a machine. And so this is a position paper for PMLR. Is machine learning good or bad for the natural sciences? Just the thing to get your blood boiling, right? Okay, so let me just read the beginning part of the abstract. Machine learning methods are having a huge impact across all the sciences. However, machine learning has a strong ontology in which only the data exist, and a strong epistemology in which a model is considered good if it performs well on held-out training data. These philosophies are in strong conflict with both standard practices and key philosophies in the natural sciences, so on and so forth. So why is this an inspiring paper? It's inspiring because I think it's at some fundamental level correct. And it's infuriating because at some level it's fundamentally correct and kind of going against this Centaur science approach that I want to advocate for. So this is my cartoon attempt, my attempt at a cartoon summary of David and Soledad's argument. So basically what they're saying is that what exists if you're a machine learning practitioner is just the data. The data is primary. Whereas in the natural sciences, we think about things that aren't just the data. I talked to you about quarks and gluons. Those are concepts. And in my brain, they exist. Quantum field theories exist. That's not data. I can't see a quark or a gluon, but somehow it exists in my mind. The strong coupling constant, the strength of the strong force, that's a latent structure. It's a hidden structure. I can't see it in the data directly. I can infer it, but it doesn't have an existence. To a machine learning practitioner, what does success look like? Success looks like accurately modeling your data. So if you have a data set and you can mimic that data set, then you've done a good job. You can take all the text on the internet, and if you can have a chatbot that responds like all the text on the internet, for better or for worse, then you've done a good job. Whereas the natural sciences, what we want is understanding. We want to understand the fundamental principles that are governing the universe. And even if we don't model things perfectly accurately, we're happy if we can get an understanding. Okay, these things are in strong conflict, at least seemingly in strong conflict. And so imagine that someone could build you a generative model, basically a way of synthetically generating all the LHC data. What if you generate synthetic LHC collisions that were indistinguishable from real LHC data? According to Haag and Villar, this would conflict with the epistemology of the natural sciences, because just because you can do mimicry doesn't mean that you have understanding, and that is correct. On the other hand, what if you could generate synthetic LHC collisions based entirely on first principles quantum field theory calculations? If you had that, that would be absolutely amazing. We are nowhere from being able to do this, nowhere near. And so we're stuck, right? You either do machine learning, which you can do accurate modeling, which you can do, but you haven't learned anything, or you can do first principles calculations, but they give you very limited information about the way the universe works. And somehow in my brain, it's yes and. I should be able to do both of these things. Centaur science can combine models of LHC data for the full phase space, everything, every pi and k on where it could go, with first principles predictions whenever they're available. Is this possible? And I would say the answer is yes, and this is forthcoming work, not yet available, but something I'm excited about, which I'm going to tell you about today, and it connects in a fun way to the recent Nobel Prize. So this is the last part of the story for today. So we're going to take inspiration from Boltzmann machines. Hinton got the Nobel Prize for Boltzmann machines. Boltzmann himself did not get a Nobel Prize for Boltzmann factors, but we're going to follow where the Nobel Prize went to. But what a Boltzmann machine is a generative model. I can generate synthetic data that samples according to a particular statistical distribution, a statistical distribution that's based on energies of particles that have spin, and the interactions of those spins. And the probability density has this exponential form, and this exponential form is known as a Boltzmann factor, and this appears all the time in the context of thermodynamics. So what is this Boltzmann factor? How do you read this? So this e to the minus e over t, the way to read that is to focus on the e. So if you guys have an exponential and there's something in the exponent that has an e, that's saying that that is a constraint on the average energy of your system. And that's what a Boltzmann factor is. It's saying that I have a statistical ensemble with varying degrees of energy, but I'm going to leave the average energy fixed to some value. And then what you do is, in an information theoretic sense, you maximize the entropy of this configuration subject to the constraint on the average energy, and that's what gives you the Boltzmann distribution. So we want to do somehow the same thing, but now for a different type of context. We want to say, look, there's certain things that I have constraints on. I have constraints on knowledge from fundamental physics. But then everything else, whatever, maximum entropy, whatever. It turns out that you have to be a little bit more careful. Particle physics data is not discrete, it's continuous. So you need to have a prior. But if I go from spins to continuous phase space and entropy to relative entropy, what it's saying is that I could predict the probability distribution of something happening at a collider by taking a prior, some guess, maybe it's coming from a machine learning model that I may or may not trust, but then constrained by things in the exponent where, for the experts, these beta things are called Lagrange multipliers. Those are imposing the constraint. And then the constrained quantity is whatever information that I have from a theory calculation. And this is the synthesis. This is literally in one equation, Centaur science. Okay? And you say, okay, this looks good, but what does this have to do with real QCD calculations? And this is where QCD theory meets information theory. So this is now plucking a random QCD calculation that I happen to have done, and I'm only choosing it because it's relatively simple, fits on one line. Okay, what are we looking for? We're looking for exponentials, something getting exponentiated. Okay, so where do I see exponentials? See an exponent there, you have to trust me as a domain scientist, ignore that exponential. Another exponential here. That's the important one. What's the thing inside of it? This thing R is called a radiator. And then you need to find what's the most important part of that radiator. Trust me, this factor here, that's not the thing that's important. It's that L. That's the important thing. It's L squared, ignore that B. Again, domain knowledge. And that L is a logarithm. Okay, so now we're primed to know what we're supposed to look at. Exponential of something log squared, okay? And that somehow needs to be related to information theory. So if I tell a QCD theorist this formula, they'll say, well, Jesse, good, that's just a next to leading logarithmic calculation. Okay, logarithmic. Next to, that's where this second exponential, which you can ignore, is coming from. It's simplified, not including all the physics effects. Jesse, why are you showing an inaccurate equation on a slide? Don't you know you need to do things more accurately? Fine, no, we just want to focus on the most important thing. Thank you, theory colleagues. That's not the point. Okay, to a machine learning practitioner, this is an opportunity for neurosymbolic learning. Like, ooh, I have exponentials, I have gamma functions. Maybe I can actually build a network architecture that actually find those analytic structures and actually build this thing from some kind of optimization scheme. But now that you've known where the exponential is, to a Centaur scientist, this exponential is called a Sudakov form factor. It's a kind of Boltzmann factor where, and now again, going off into technoland, where the cusp anomalous dimension is the Lagrange multiplier, that's this thing up here, that enforces a constraint on the second logarithmic component, that's at L squared here, of the distribution. And this realization, I fell out of my chair when I was having this realization. Now to you, you're like, whatever, it's the second logarithmic moment of a distribution. Who cares? Well, QCD has been around for decades. No one has ever thought to compute the second logarithmic moment of these distributions. They calculate regular moments. No one thought to do logarithmic moments. Whereas in this framing, that is clearly the information that you should have computed. And so with my collaborators, Ben Ossi, Kyle Lee, and Stefan Höcke, for the first time, we have calculated a QCD calculation of, it says thrust moments, it should say logarithmic thrust moments, that's the important part. And here we have theoretical calculations, making predictions that for some reason no one thought to do before. And now we can do the Centaur science merging. We can take priors from imperfect generators, things which you can imagine this coming from an untrustable machine learning architecture, and then constraining it using this reweighting factor, these Boltzmann factors. And what you see is this stuff, like when people say, I can't trust the machine, it hallucinates. You can think about the deviation between these curves as being types of hallucinations, but when you put in first principles knowledge, they constrain down, and then you get trustable knowledge coming out. And what I didn't have time to put in the slide is getting an update from my collaborators, again, this is an ongoing project, where you can actually do different projections, and for projections that are nearly in the same direction as the thing you're constraining, you also get this smushing down, constraining the uncertainties. But in directions that are in some sense perpendicular, you find that the uncertainties don't shrink, which makes sense because you haven't provided the theory input. So it behaves in the way that a theorist would like. You do the calculation, you get better results. If you haven't done the calculation, then you know what calculations to do in the future. And so this is, again, continuing the tradition of relating properties of physical systems to in computation and information theory, and an example of the benefits of taking this kind of twin approach to thinking about AI and science. So with that, we're going to open up questions in a moment. So let me just review. I told you a little bit about the Centaur science approach and why it's well suited to the field of particle physics, and maybe you've been convinced that it might be well suited to your field as well. I told you about putting space-time symmetries into transformers, taking an architecture that works really, really well, but embedding physics knowledge into it. And then the benefit for me of thinking like a machine. And when I thought like a machine, I saw something that I didn't even see in my original physics calculations of what's actually most important about the equations that I previously computed. And it seems like we're going to see more advances in this field coming from this intersection, which again is why it's, here I was talking about my own work in this setting, but some other time I can tell you about all the other great things that are happening at this Institute for Artificial Intelligence and Fundamental Interactions, thinking about AI as a pathway to scientific insights, but also physics intelligence as a pathway to AI innovation. And then just to emphasize it again, this progress in this interdisciplinary space driven by early career talent with interdisciplinary training. And I've benefited hugely from my collaborators who are younger than me and bring more enthusiasm and knowledge than me. And it's a pleasure to be able to share their work with you today. Thanks very much.